Welcome back to our second tutorial. In this tutorial, we're going to be diving into the exciting world of robotics. We will guide you through the process of creating and controlling a self-balancing robot. We will first add all the components required to set up the robot, and then after that, we are going to write our own custom script that will control its movement. Let's get started. Start by downloading the CAD file for the robot from our website and import it into the model. Make sure that Center Transforms is enabled, as this will make things a lot easier for you. The robot appears to be oriented incorrectly. We'll first apply a -90-degree rotation about the x-axis. Next, we'll move the robot up by 0.14 meters and center the Z component. Very good. Now select the body entity and add a physics component. Alright, only thing we need to change here is to set the mass to 2 kilograms. Now select the wheel, and let's add physics to that as well. This time we'll set the collider type to convex and the mass to 0.5 kilograms. Click this little button to add a joint and configure the constraint so that it is a revolute joint. Because we centered the transforms earlier, we don't actually need to change the anchor point here, nor the axis either. They are already configured correctly. We need to ensure the wheel is attached to the body, so select the body as the base. Click the button to add a motor component, which is automatically bound to the joint. Set the controller of the motor to velocity and the torque limit to 10 Newton meters, since this will eventually be controlled by our script. Set the target velocity to 0 and the target acceleration and deceleration to 3,000 degrees per second squared. And finally, set the stall action to none. Alright, all done. We've finished with this wheel now, but we need to set up the other wheel as well. The properties of each wheel should be identical, so let's just go ahead and set up the other wheel. A small trick you might not know is that you can right-click to negate the direction of the axis. Perfect. Now play the simulation so we can make sure that everything seems to be okay. Now that we are done setting up all the components we need, we're ready to start creating our script. Click the button to create a new file for our script. I'll call it controller, but of course feel free to replace it with any suitable name. The first thing I'm going to do is declare the dependencies for each motor as public properties. I'll use handles to reference these dependencies. Remember, handles monitor the lifetime of the objects they reference. I'll also create a property for the maximum speed of each motor and use a decorator to set the unit type to angular velocity. Next, I'll create a private variable called balancer. This will use the PID controller class in our API to balance the robot at a given angle. Now go ahead and initialize these properties in the constructor. Set the max speed of each motor to 4,000 degrees, which will convert to an angle specified in radians, and instantiate a new PID controller for the balancer. The PID controller stores 3 constants: the proportional gain, integral gain, and derivative gain. The proportional term is proportional to the current error. It acts to reduce the difference between the set point and current value. Set this value to 1000. The integral term accumulates past errors over time. We won't use the integral term in this tutorial, so set the value to 0. The derivative term anticipates the future trend of the error by measuring its rate of change, which will help increase stability and reduce overshooting. Set this value to 100. Next, we'll go ahead and create the update function, which will get called every time step. I'll create a target angle constant and set it to 5 degrees. Now make the set point of the balancer PID controller equal to this target angle. We need to calculate the current angle of the robot. We'll use the signed angle unit function to help us with this. This angle is measured from the z-axis of the robot's world rotation to the up axis in the YZ plane. Next, we will call the evaluate function to calculate the control output of the balancer's PID controller, passing the measured angle of the robot as the current value as well as the time step. Since the range of values this function returns can be very large, we'll clamp the output so that the absolute value is less than the max speed. The last thing we need to do is set the target velocity of the motors, driving each wheel to this calculated value. Great. Save the script and switch back to the editor. Select the body entity and add our controller component to it. Configure each of the two properties we defined for the motors driving each wheel. Now we're ready to play the simulation. Let's see what happens. Okay, this is excellent. The robot is in motion now and is tilted at approximately 5 degrees. Let's go back into the script editor now and change the target angle to -5 degrees. Okay, everything appears to be working correctly. The last thing I'll do is set the target angle to 0 degrees. Perfect. Now that we've got the robot balancing correctly, I'd like to get it to move to a particular target position. This is going to require us modifying the script again. Go ahead and open the script editor. Create a new private variable called positioner. We will use the PID controller class again, but this time to control the position of the robot. Instantiate a new PID controller for the positioner in the constructor. I've already gone ahead and tuned the proportional, integral, and derivative gains for this controller. Set the proportional gain to 0.5, the integral gain to 0, and the derivative gain to 0.35. We need to measure the current position of the robot. Given that the robot's movement is confined to a single dimension, we only need to get the z component. For the target angle, we will call evaluate on the positioner PID controller, passing the measured position as its current value and the time step as well. We will feed the output of the positioner controller into the set point of the balancer controller. Remember, the range of values this function returns can be very large, so we'll need to clamp the output again to ensure that the absolute value of the target angle is less than 8 degrees. We also have to negate this value because of how we measured the signed angle below. The last thing we need to do is create a public property for the set point of the positioner controller. We will use this property to set the target position of the robot through the inspector. This will allow us to change the target position whilst the simulation is running. We need to create both a public getter and a setter to get this working correctly. Okay, I think we're done with scripting now. Go ahead and save your script and switch back to the editor. Notice that the target position property we just created is visible through the inspector. Now I'll go ahead and play the simulation. Set the target position to 1. Awesome. Everything appears to be working exactly as intended. At this point, feel free to go ahead and interact with the robot now. Our control logic is basically complete. There's not much more we need to do from here. I'm just going to continue changing the target position to see how the robot responds. If you want, you can also mess around with the constants we baked into the script. You can try changing the maximum tilt angle, the max speed of the motor, and the gain constants of the PID controller. One last thing I'm going to do is modify the graphics materials of the robot to make it look more realistic. That completes our tutorial. I hope you learned something new. Thanks for watching.